Hi friends, welcome to our YouTube channel Knowledge Academy. The main aim of this lecture is discuss about the TS Genco-2015 Solutions of 2015 question paper of electrical engineering in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button so whenever you upload a new video, the direct notification comes on mobile. If any improvements in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. So now we are going to solve the first question. See the question here. The equivalent series resistance of a capacitor C in terms of its power factor and the operation frequency is given by. So here we have to find what is the equivalent resistance, the equivalent series resistance of a capacitor C in terms of its power factor and the operation frequency we need to figure out. So what are the four options? Option A is the correct solution of this question. It means we have to write the resistance in terms of the power factor and the frequency and the capacitance value. We have to write one equation. So therefore, out of the four options, option A is the correct solution of this question. So let's solve this numerical. So in this question, basically there is a capacitor. So for this capacitor, there is a small amount of resistance, which is R, and C is the actual capacitance of a capacitor. So here they are going to apply a source of voltage Vs and a supply frequency of F. So now we have to write a relation between the resistor, power factor and the capacitor value. So we have to write a relation with respect to R in terms of the power factor and the capacitance value. We need to figure out a relation. So here this is R, as this is a series RC circuit. So this is the current which is going to flow through this circuit. So now I am going to assume the current as the reference phasor. So when we are going to assume the current as a reference phasor, always in the resistor, the voltage across the resistor and the current in the resistor are both in phase. So therefore, this is the voltage across the resistor, which is VR. So therefore, VR and the current are both in the phase. But if you see here, in the capacitor, the voltage across the capacitor is VC. So all these are the RMS values. So therefore, always in a capacitor, the current is going to lead, whereas in inductor, the current is going to lag. So therefore, in a capacitor, the current is going to lead the voltage across the capacitance by 90 degree. So therefore, as the current is going to lead the capacitance voltage by 90 degree, it means that the voltage across the capacitor should lag the current by the 90 degree. So this is the voltage across the capacitor is going to lag the supply current by 90 degree. So now, as these are VR and VC, then the Vs is the net voltage, or we can say this is the supply voltage is the vector sum of the voltage across the resistor and the voltage across the capacitor. So by vector addition, so this is a line which is going to get you about the supply voltage Vs. So here now, if you want to know what is the power factor angle, which is the power factor angle is the angle between the supply voltage and the supply current. So phi is the angle between the supply voltage and the supply current. So phi is called as the power factor angle. So I want to write a relation which is cos phi. Cos phi is the power factor which is based by the hypotenuse. So therefore VR by Vs. So VR is nothing but voltage across the resistor, which is I into R, and supply voltage is nothing but I into mod of Z, where the total impedance of the circuit Z is equal to R minus JXC. But if I want to know what is the magnitude value, then which is under root over R square plus XC square. So now here I get cancels because it is a common term. So then we are going to get R by mod of Z. So is equal to R by mod of Z is under root over R square plus X square. See, as this is a practical capacitor, so practical capacitor is going to have a resistance and also capacitance. So in a practical capacitor, the resistance will be a very small value. So therefore, we are going to assume that R, the resistance of the capacitor, is very small. See, if R is very small quantity, and if you are going to do the square of a very small quantity, then we are going to get a still smaller value. So therefore, here if you take R as a small and if you take the square of it, means if you take a small value and if you do the square of it, it is going to be lesser than the R. So therefore, it is a very small value. So therefore, now we are going to neglect this R square, means we are going to assume it is nearly equal to 0. So therefore, wherever R square is there, we are going to blindly keep it as a 0 value. So therefore, here finally we are going to get power factor is equal to R by under root over, as in place of R square we are going to make it 0. So therefore, the only term which is available is x square. So therefore, under root over x square. So therefore, this square root and 2 gets cancelled. So therefore, finally we are going to get R by XA. So now I want to write R in terms of cos phi into Xc. So therefore R is equal to Xc into cos phi, where Xc is equal to the capacitance reactance of the capacitor value, which is 1 by omega c into cos phi. So finally we can write cos phi by omega is equal to 2 pi f into c. So cos phi is called as a power factor. So power factor by 2 pi fc. So finally we got a relation R is equal to power factor by 2 pi fc. So this is the relation of R in terms of the power factor and the frequency and the capacitance value. So this is the correct solution of this question. So now we are going to solve the second question. See the question here. A network contains linear resistors and ideal voltage sources. If values of all the resistors are double, then the voltage across each resistor will be. So in this question they are telling about if the voltage, so there is a network which contains the ideal voltage sources and a lot of resistance. So if the resistance of each and everything which is double, then what will be the voltage across each and every resistor, they are asking. So out of the four options, option D, not change, means the voltage is not going to change. So this is the correct solution of this question, which is option D. So let's solve this numerical. Now I am going to assume a very simple circuit. It's a very simple circuit of only two resistors and ideal voltage source. So the voltage across the resistance R1 is V1 and the voltage across the resistance R2 is V2. It's a very simple circuit of one ideal voltage source and two resistance. So I want to know what is the voltage across each and every resistor. So by using the voltage division principle, we are going to get the voltage across each and every resistance, which is V1 is equal to supply voltage into resistance R1 by R1 plus R2, and similarly V2 is equal to Vs into R2 by R1 plus R2. So these are the expressions based on the voltage division principle. So now in the second case is the case 1 and the case 2 is now we are going to change the resistance to double value. So each and every resistor value we are going to double its original value, but we are not going to change the supply voltage. Supply voltage remains as a constant value. So therefore supply voltage will be there as the previous one, but only the resistance values are we are going to double it. So it is 2R1 and 2R2. So now the voltage across this new resistance I am going to assume, which is V1 dash and V2 dash. So therefore now I want to find this V1 dash and V2 dash. So with the help of voltage division principle. So therefore V1 dash is equal to Vs into 2R1 by 2R1 plus 2R2. So if you simplify this circuit, this equation, we are going to get V1. So which is nothing but the previous one. So therefore now V2 dash is equal to, so Vs into 2R2 by 2R1 plus 2R2. So if you solve this one, we are going to get again V2. So finally we are going to conclude that V1 dash is equal to V1 and V2 dash is equal to V2. It means that even if you changing the resistance to a double value, still we are going to get the same previous voltage, which is V1 and V2. So this is a correct solution of this question. So now we are going to solve the third question. See the question here. In a series RLC high Q circuit, the current peaks at a frequency. So in the series RLC circuit, so we need to find at what frequency we are going to get a maximum value of the current. We need to figure out. So from out of these four options, which is equal to the resonant frequency. So basically at the resonant frequency in a series RLC circuit, we are going to get the huge amount of current or maximum current in the circuit. So let's solve this numerical. So this is basically a series RLC circuit. So of supply voltage Vs and the frequency F. So this is the current in the circuit. So now what we are going to do is we are going to vary this frequency. So we are going to vary this frequency from 0 to very huge value, and then we are going to see what is the value of the magnitude of the impedance of the circuit and also the current in this circuit. So if you do that one, finally we are going to get, these are the two graphs we are going to get, which is this is the magnitude of the impedance of the circuit and this is the current in the circuit. So if you see at a particular frequency F0, which is called as a resonant frequency, at this frequency we are going to get a minimum value of the impedance. So if the value of the impedance is very low, it means current is equal to voltage by resistor. So voltage by impedance, as the impedance itself is a very low value at resonant frequency, so therefore the current we are going to get a very huge value. So therefore at particular frequency, at resonant frequency, the circuit will be purely resistive. So that is called as a resonant frequency. At a frequency, resonant frequency, the circuit will be a purely resistive circuit. It means we can say that the phase angle between the supply voltage and the supply current is 0 degree, or we can say it is a unity power factor circuit. So this is and finally this is the diagram of the current in the circuit. This is a current diagram in the circuit. So at resonant frequency we are going to get a maximum current, and these are the frequencies which is FL and FH, which are called as a low. FL is called as the low half power frequency and FH is called as the high half power frequency. So therefore here it means that this is the maximum value of the current at resonant frequency, and at FL and FH we are going to get a I maximum by root 2. It means that here, suppose if the power in the circuit at resonant frequency is P, then at FL and FH we are going to get a power in the circuit which is P by 2, means half of the power as compared to the maximum value. This is the true meaning of this one. So now what we are going to discuss is some important relations. Now we are going to discuss, which is F0 is equal to under root over FH into FL. So we can say that resonant frequency is the geometric mean of the FL and FH, which is F0 is equal to under root over FH into FL. So now I want to discuss what is the nature of the circuit at different frequency ranges. So basically for 0 less than F0, so when the frequency is going to lie in this region, which from 0 to F0, what is the nature of the circuit? So at these conditions the capacitance effect will be more than the inductive effect. So therefore the overall circuit will act like a capacitive circuit, means leading power factor. So therefore for a frequency range of 0 to F0, the capacitance effect will be huger when compared to inductive. So therefore the circuit will be a purely capacitive, means the power factor will be a leading fashion. And similarly here at F0 the inductive reactance will be equal to capacitive reactance. So therefore the circuit will be purely resistive. So therefore we can say that at F is equal to F0, that resonant frequency, the circuit will be purely resistive, means we can say it is a unity power factor circuit. So therefore the phase angle between the voltage and the supply current is 0 degree. So therefore here when the frequency is more than resonant frequency, when we are going to operate frequency which is more than the resonant frequency, then the inductive reactance will be very higher than the capacitive reactance. So therefore the circuit will act like an inductive circuit or lagging circuit. So therefore at a frequency greater than resonant frequency, the circuit will act like an inductive circuit, or we can say which is a lagging circuit or lagging power factor circuit. And also in AE examinations they will ask in the questions what is the power factor at the FL and FH, or at F0 they will ask in the questions. So it is better to remember these values. So therefore in order to save the time, so the power factor at the lower half power frequency, which is 0.707, because it's a leading circuit at frequency less than F0, so therefore it is a leading power factor. And similarly the power factor at the higher half power frequency, which is 0.70, lagging, because at a frequency greater than F0 the circuit is a lagging. So therefore it is 0.707 lagging. And also the power factor at the resonant frequency, so at resonant frequency the circuit is purely resistive, so therefore the power factor is a unity power factor. So this is a unity power factor. So basically in the question they have asked at what frequency the current will be a maximum value in the circuit. It means at resonant frequency the current in the circuit will be a very maximum value, because at that instant the circuit is a purely resistive one. So now we are going to solve the fourth question. See the question here. A DC voltage source is connected across a series RLC circuit. Under steady state conditions the applied DC voltage drops entirely across the. So basically this is a series RLC circuit. So for the series RLC circuit we are going to give a DC supply voltage. So at steady state condition, so the DC voltage drops entirely across the, means the supply voltage will drop entirely across which element, whether R, whether resistor, whether inductor, or whether capacitor, we need to figure out. So what are the four options? Option C, the capacitor only, means the supply voltage will drop purely across the capacitor itself. So let's solve this numerical. So this is a series RLC circuit. So for this series RLC circuit we are going to give a DC voltage source as the input voltage. Then in this question they are asking at steady state the voltage, the supply voltage will drop entirely across which element, whether resistor, inductor, or capacitor, we need to figure out. So basically now we are going to analyze this circuit only at the steady state condition, means after a lot amount of duration. So at a steady state what is going to happen? So basically the inductor, so when we supply any DC voltage across the inductor, what is the nature of the inductor at a steady state? So inductor at a steady state means the current will be a very constant value. value. So at a steady state, the current in the inductor will be a constant value, which is, so for inductor element, the current will be a constant at a steady state. So we know the voltage and current relation across the inductor, which is voltage across the inductor is equal to L into di by dt. As the current itself is a constant value, means the derivative of the current will be a 0. So therefore, the derivative of the current will become 0. So therefore, the voltage across the inductor will be 0 at steady state. Means if the voltage is 0, means we have to do a short circuit, because only at short circuit condition the voltage will be 0. So therefore, that is the reason we are going to do a short circuit. And now I want to know what is the nature of the capacitor at a steady state. So therefore, see, at the capacitor, always at a steady state the voltage will be constant. So the voltage across the capacitor at a steady state will be constant. So now what is the relation between the voltage and the current in a capacitor, which is I is equal to C dV by dt. As the voltage is a constant at a steady state, so derivative of any constant will give you 0. So therefore, at a steady state the current in the capacitor will be 0. So if you want to write a current as 0, then we have to do an open circuit, because only at open circuit the current will be 0. So therefore, the capacitor has to be replaced by open circuit at steady state, and the inductor has to be replaced by short circuit at steady state. So that is the thing we are going to do now. So therefore, this is the actual circuit. So now I want to know what is the behavior of this circuit at steady state. So therefore, the resistor will be again still a resistor, but here the inductor and capacitor, so inductor is replaced by short circuit and the capacitor is replaced by open circuit, because at a steady state the voltage across the inductor is 0. So we are going to do a short circuit, and the current in the capacitor is 0 at steady state. So therefore, we are going to make a open circuit. So if you analyze this circuit, so let me assume this is the voltage across the resistor, and this is the voltage across the inductor, and this is the voltage across the capacitor. So at steady state conditions, so therefore this is the current in the circuit. As it is an open circuit, the current in the circuit will give you 0 value. So therefore, the voltage expression of across the resistor, which is I into R, as I is 0, so therefore the voltage across the resistor is also equal to 0 volt. And similarly, so VL is nothing but it's a short circuit. So therefore, the voltage across the inductor will be again 0. But see, VC, it's an open circuit. So whatever the voltage across the supply will go across the capacitor voltage. So therefore, the capacitor voltage is equal to supply DC voltage. So finally, we have concluded that here at a steady state in a series RLC circuit, the voltage across the capacitor will have the DC voltage, means the applied DC voltage will purely goes across the capacitor at a steady state. So now we are going to solve the fifth question. See the question here. The core of a transformer is made of. So basically the core of a transformer is made of which material? Option A, silicon steel. Option B, annealed copper. Option C, seasoned wood. Option D, aluminium. So what are the four options? Option A, which is the silicon steel, is the correct solution of this question. So let's discuss something more about this one. So now we'll discuss why the silicon steel is used as a core material for the transformer, because silicon steel has different names. So some of the different names of the silicon steel, which is electrical steel or lamination steel or silicon electrical steel or relay steel or transformer steel. These are some of the different names of the silicon steel. So basically the silicon steel is called as it is a ferromagnetic material. So it is a ferromagnetic material, means here we can get the magnetization in a very easy manner, and also even if you are not going to give any supply, after removing the supply, still it is going to hold the magnetic properties. That is the best advantage of the ferromagnetic material. And also the relative permeability of silicon steel is very high, and the relative permittivity value is nearly equal to 4000, means even a small amount of excitation can give you a huge amount of flux in the core. So therefore that is the true meaning of this one. And also the reluctance of the silicon steel is very low, and also the hysteresis loop area is very low, means the hysteresis BH curve loop area is low. It means that there is a small hysteresis loss, even because the area of the BH loop is going to tell you how much amount of the loss in the dipoles. So this area itself is low, it means it is going to give you a small hysteresis area. It means small hysteresis loss also. As hysteresis loss are very low, so therefore the core loss is also very low. So therefore here, and also silicon steel is going to contain two important components, which are the iron and a silicon. So iron is going to have percentage of 96.8% and the silicon is about 3.2%. So basically silicon steel is a combination of the iron and silicon. So by adding silicon to iron, the important things we are going to get is the resistivity of the material is going to increase. So by adding silicon to iron, the resistivity of the silicon steel is going to improve. So because of this reason, so as resistivity increases, the eddy current losses also increases. So if any material, if the resistance is very higher, means if the resistance property is increases, it means the eddy current loss is also going to decrease. So these are some of the important aspects of the silicon steel. So because of the silicon steel, the advantages which are the core loss is very low, means the hysteresis loss is very low, and also this losses and also the eddy current loss is also very low. So therefore the core loss is also very low, and the relative permeability value is very high, which is nearly 4000. So even a small amount of excitation of the voltage, we are going to get a huge flux is going to flow in the core. And it is also a ferromagnetic material. So if you off the supply, then also this material is going to hold the residual magnetism. So these are the important aspects of silicon steel. So because of all these advantages, this silicon steel is used in the transformer core. So now we are going to solve sixth question. See the question here. The number of independent loops for a network with n nodes and b branches is. So here now we have to write the relation between the number of loops, branches and nodes. So therefore out of the four options, option C is the correct solution of this question. So let's solve this numerical. So basically this question belongs to the graph theory in the networks, which is n represents the number of nodes in the graph and also b represents the number of branches in a circuit. So L, it is going to represent L is called as the number of links, or it is also called as the chords, or the number of independent loops, or it is also called as a chord tree, or the branches of these links. So it is called as a chord tree. So therefore now what is the relation between the L, B and number of twigs? So basically L is equal to total number of branches minus number of twigs, where n minus 1 is called as the number of twigs. Twigs are nothing but the number of branches in a tree. The branches in a tree are said to be a twigs. So therefore the number of independent links or loops is equal to total number of branches minus number of twigs, which is n minus 1. So if you solve this one, we are going to get b minus n plus 1. So this is the relation between the L, B and n. So here, and some other interesting concept is here, number of twigs or branches of tree. So whatever the branches in a tree are called as a twigs, and if you want to know number of twigs, which is number of nodes minus 1. So therefore the total number of branches minus number of twigs, we are going to get the number of links. So L is also called as the L, it is going to give you number of independent mesh equations. So L, it is going to give you number of independent mesh equations, and number of twigs, it is going to tell you number of independent node equations. So therefore these mesh equations are, it is responsible for the mesh analysis, and number of node equations which is responsible for the nodal analysis. So if you want to know on which analysis, if you want to solve a network, if these two, based on these two, which is going to give a lower value, so based on that you have to prefer that analysis for a circuit. Suppose if it is giving a value of 4 equations and if it is giving a value of 3 equations, so here for a given circuit, if L is equal to 4 and n minus 1 is equal to 3, suppose if you are going to get like this, then for that circuit the 3 is very lesser than 4, so therefore it is preferred for the nodal analysis rather than the mesh analysis. So based on these values also we can know which analysis is preferred for a given circuit. So therefore this is some of the important points for this question also. So basically in the question they are asked what is the relation between the L, B and N, which is L is equal to B minus N plus 1. This is the correct solution of this question. So now we are going to solve the seventh question. See the question here. Two two-port networks are connected in cascade. The parameters of the network are obtained by multiplying in individual. So in which two-port networks, so we are going to multiply the parameters. So what are the four options? Option D in ABCD parameters, or we can say it as T parameters. So in ABCD parameters or T parameters, so if there are two-port networks are in cascade, then the net two-port parameters will be, it is a product of the individual parameters. So option D is the correct solution of this question. So let's discuss something more about this one. So when two-port networks are connected in series fashion, means the current in this one is very same, it is I1, and current here it is always I2. Means when the two-port networks are connected in series, the net equivalent impedance of this two-port network will be summation of the each individual two-port network, which is Z1 plus Z2. Suppose if the two-port networks are connected in parallel, means the voltage across this one is same and the voltage across this one is same, and similarly voltage across V2 is same across this and this. So therefore we can say these two-port networks are connected in parallel, then the net impedance or net admittance will be equal to summation of the each and individual admittance. This is for the when the two-port networks are connected in parallel fashion. Suppose if the two-port networks are connected in cascade, means output of one two-port network is the input to the other two-port network, then the net equivalent T parameters or the ABCD parameters is equal to product of the individual T parameters. So therefore this is for the cascade and this is for the parallel and this is for the series fashion. So therefore in the question they asked about the cascade. So therefore it is a product of the T parameters, or we can say it is a ABCD parameters. So the net equivalent ABCD parameters is equal to product of the individual ABCD parameters of the two-port network. So this is the correct solution of this question. So now we are going to solve the 8th question. See the question here. A moving coil ammeter has a fixed shunt of 0.02 ohm resistance. If the coil resistance of the meter is 1000 ohms, a potential difference of 500 millivolt is required across it for full scale deflection. Under these conditions, the current in the shunt would be. So in this question, they are given a shunt resistance and also meter resistance, and they are also given at what voltage we are going to get a full scale deflection also. In this question they are given. So now based on these three data, we need to find what is the current in the shunt resistance. We need to figure out. So what are the four options? Option C, 25 ampere is the correct solution of this question. So let's solve this numerical. So this is a circuit for a PMMC, permanent magnetic moving coil. So it is a moving coil ammeter. So it is going to consist of the meter resistance and the shunt resistance. So in the question they are given the shunt resistance is 0.02 ohm and the meter resistance is 1000 ohm. So here if this is the total current I, or we can say it is a circuit current also, and IM is called as a meter current and IS is shunt current. So in the question they are also given for a voltage of 500 millivolt we are going to get a full scale deflection, means the ammeter is going to give you a full scale deflection for this voltage across this circuit, across these two elements. So now in the question they are asking what is the current through the shunt resistance we need to figure out, means ISH we need to figure out. So basically by using the Ohm's law, the voltage across the RSH we know, which is 500 millivolt, and the resistance value we know. Only thing we have to know what is the current. So therefore voltage is equal to current into resistance. So current is equal to voltage by resistance. So shunt current is equal to Vm by RSH. So Vm is equal to voltage across the shunt resistance, which is 500 millivolt. So 500 into 10 to the power of minus 3, and the resistance of the shunt resistance is 0.02. So if we solve this one, we are going to get 25 ampere. So therefore this is the current, this much amount of ampere of current is going to flow through this shunt resistance, which is ISH is equal to 25 ampere, and this is a correct solution of this question. So now we are going to solve the 9th question. See the question here. An unshielding moving iron voltmeter is used to measure the voltage in an AC circuit. If a stray DC magnetic field having a component along the axis of the meter coil appears, the meter reading would be. Suppose in this question they are given a unshielding moving iron voltmeter. So here from externally we are going to supply some magnetic field along its axis. Then what is the effect on the reading, whether it is increased or whether it is decreased, we need to figure out. So what are the four options? Either decreased or increased depending upon the direction of the DC field. So option D is the correct solution of this question. So now discuss something more about this one. So basically in the moving iron voltmeter we are going to use the electromagnet, means these are the two poles. For this we are going to give a winding here. So with the help of winding we are going to give a DC supply for this winding. So therefore this winding get energized. So therefore here by using the right hand rule we are going to get a magnetic field in this direction. So because of this magnetic field and the supply there will be deflection in the meter. pointer. So therefore pointer in the meter. So because of this reason only there will be deflection in the pointer of meter. So but what happens now here, suppose shielding is provided. Shielding means a protection. So therefore this magnetic field, the magnetic field which is present inside, let me assume this is B1. So if you are going to provide a shielding here, so what is going to happen? Suppose if you are going to provide a shielding, so therefore the external magnetic field is not going to enter inside the meter. So therefore if external magnetic field is not going to enter inside the meter, then nothing is going to happen. But in the question they have mentioned the shielding is not provided, means there is no shielding effect. So therefore shielding is not even present. So now the external magnetic field can affect the internal magnetic field. So let me assume, suppose here the magnetic field, the external magnetic field I am going to produce in this direction, which is B2. So therefore this is going to enter inside. So B1 and B2 are in same direction. So therefore here a net magnetic field is equal to B1 plus B2. So because of this reason the pointer will rotate in a huge fashion. So therefore the pointer will read a huge value. Suppose if the magnetic field, the external magnetic field is in the opposite direction than the original one inside magnetic field, then these two are in opposite direction. So therefore the magnetic field now decrease. So net magnetic value will decrease. So because of this reason the pointer will read a low value. So therefore based on the direction of the magnetic field with respect to the inside magnetic field, the meter reading can increase or decrease. So in the question they have not given the directions of the B1 and B2, whether B2 is along the B1 or opposite of B2, they have not particularly mentioned. So we can say that the reading can be either increased or decreased. If they are in same direction, then the meter reading will increase. If they are in opposite direction, then the meter reading will decrease. So this is the conclusion from this one. So shielding has to be provided in order to protect from the external magnetic fields. If the shielding is not provided, yes, because of external magnetic fields there will be effect of the internal magnetic field. So therefore the pointer movement can be changed, either increased or decreased depending upon the direction of the external magnetic field, whether it is along the B1 internal magnetic field or whether it is opposite to the internal magnetic field. So this is all about the conclusion. So if there is no shielding effect, so whether the reading can be increased or decreased based on the direction of the B2, whether it is same direction of B1 or opposite to B1. So now we are going to discuss the last question of this lecture. See the question here. A DC voltmeter has a sensitivity of 1000 ohm per volt. So when it measures off full scale in 100 volt range, the current through the voltmeter is. So in this question they are giving that basically the sensitivity of this meter, of this voltmeter is 1000 ohm per volt, and the full range of this meter is 100 volt. Suppose if this same voltmeter is going to measure half of the full scale, means suppose 50 volt it is going to measure, then what is the current reading or current in this voltmeter we need to figure out. So out of the four options, option C, which is 0.5 milliampere, is the correct solution of this question. So let's solve this numerical. So in this question they are given a voltmeter of resistance R. So basically here the maximum voltage which can read by this voltmeter is 100 volt, and also they are given the sensitivity which is 1000. So now I want to know what is the resistance of this meter. So when we are going to apply full scale voltage, so when we are applying a full scale voltage, the current also we are going to get the full scale current, means the maximum current we are going to get. So basically the formula of the sensitivity, which is sensitivity is equal to 1 by full current. So therefore sensitivity is equal to 1 by full current. So therefore I full or maximum current. So I full current is nothing but voltage by full scale voltage by resistor. So therefore full scale voltage by the resistor. So therefore this is resistance by full scale voltage. So full scale voltage is 100 and the resistance we need to know, but we know the value of sensitivity. So therefore sensitivity 1000 is equal to resistance by full scale voltage, which is 100. So if you solve this one, we are going to get resistance is equal to 100 kilo ohm. So this is the resistance. So resistance is equal to 100 kilo ohm. So now we are going to apply half of the voltage. Suppose it is 100 volt, means half of the 100 is 50 volt. Then I want to know what is the current in the meter. So using the Ohm's law, voltage is equal to current into resistor. So voltage is equal to 50, current we need to figure out, and the resistor value is 100 kilo ohm. So if you solve this one, we are going to get 0.5 milliampere. So therefore at half scale, at half of the full load, means at half of the full load, full voltage, we are going to get a current which is 0.5 milliampere. So if I want to know what is the full current, means if you are going to give a full voltage, then what is the full current we need to figure out. So it is nothing but here as sensitivity is equal to 1 by I full current, so which is nothing but sensitivity is equal to 1000, so we are going to get a full current is equal to 1 milliampere. So in other way, if you are going to give a 100 volt, the current we are going to get is 1 milliampere, and if you are going to give a 50 volt, the current we are going to get is 0.5 milliampere. So I want to make a diagram of the pointer of the voltage scale and also the current scale. So this is the voltage 0 volt, and the maximum voltage read by this instrument is 100 volt, and the current is minimum current is 0 ampere, and the maximum current read by this instrument is 1 milliampere. Suppose if the pointer is at this position, means when we are going to apply 100 volt, we are going to get a 1 milliampere. Suppose if we are going to apply 50 volt, then we are going to get current of 0.5 milliampere. Suppose if you are going to apply 0 volt, then we are going to get a 0 ampere of current. So it is a linear scale. So therefore, if you apply 100 volt, the current will be 1 milliampere. If you are going to apply 50 volt, then we are going to get 0.5 milliampere. If you are going to apply 0 volt, then we are going to get 0 ampere. So this is the true meaning of this one. So in this question, they are asking only at half of the voltage, what is the current, which is half of the full load current, which is 1 milliampere by 2, which is 0.5 milliampere. Also we can say it in an easy fashion. So this is the correct solution of this question. So by this lecture, we have successfully completed the 10 questions, which are the previous year questions of the TS Genco-2015 Solutions of Electrical Engineering in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button, so whenever you upload a new video, the direct notification comes to mobile. If any improvements in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care, and bye bye.